Over the course of the semester, actually at the beginning of the semester, we discussed what's called the velocity distance problem, namely that if we had a displacement function of some type, how could we go about determining the velocity function? We started with displacement, and then from there we went to determine the velocity, and of course that was given by the derivative. For example, in the instantaneous velocity activity, we studied the following displacement function. Recall this, I think I was driving home from campus or running home or something like that. It recorded my displacement from Allendale measured in miles as a function of time measured in hours. And the graph looked something like this. For a while I was jogging towards my house, and then right about here, I turned around, and then I was going away from my house, and then I turned around again. And right about here, right about 4 hours, I was as close to my house as I got before I started moving back towards Allendale. Now this was the distance graph. Distance increasing, velocity, which is the derivative of distance, distance increasing, derivative, which is velocity, positive. Distance decreasing, the derivative is velocity, which is negative. Distance increasing, velocity, which is the derivative, is positive, and so on and so forth. But now what we're going to do is, well, before I say that, we also knew how to calculate the derivative using the limit formula, but then eventually we went on and we used shortcuts. So for this function up here, if I take the derivative using the appropriate shortcut formulas we talked about, we know that it's given by this formula. So the derivative of displacement is the velocity, which is this. This was the long way of doing it. This was the short, easy way using derivative shortcuts. Now what we're going to do is we're going to address the opposite problem. Namely, if we have information about velocity, we want to determine the information about an object's displacement or distance traveled. So what we're going to do in this problem is kind of like what we did for the derivative. For the derivative, we used our background knowledge that average velocity is change in distance divided by change in time. Here we're going to use the fact that distance equals rate or velocity multiplied by time. So let's take a simple example. Suppose a jogger runs at a constant rate of 5 miles per hour for 3 hours. How far does she go? Well, this is pretty easy. It's just 5 times 3, which is 15 miles. Now I've graphed the function v of t equals 5. This is positive, which means the distance, whose derivative is that, is increasing. Now this 15 can also be represented in terms of the graph. In the same way that the derivative is the slope of displacement, in this case, my distance traveled is 15, which is actually the area of this rectangle. The rectangle has height 5 and width 3. Of course, it's not to scale. So the distance traveled is equal to the area of that rectangle. Another example. Let's suppose instead of a constant velocity, the jogger moves in such a way that her velocity function is given by this. Her velocity is 4 miles per hour, and then somehow miraculously it goes down to 3 miles per hour, and then goes down to 2 hours per hour, and then miraculously up to 5.5. Of course, no one would actually jog in a way that their velocity graph looked like this, but we can use the reasoning we used a few moments ago to actually compute the distance traveled. So let's take a look at the first hour. The first hour, the velocity is constant at 4. The time was 1 hour, so the distance traveled was 4 miles. Over the course of the next 2 hours, the velocity was constant in 3. So 2 times 3 is 6. 2 times 1 is 2. 5.5, which is the velocity over this time interval, times 2 is 11. And if we add these numbers up correctly, I hope we get 23. Now this represents the distance traveled, but it also represents the sum of rectangle areas. Namely, the 4 is the area of that rectangle. The 6 is the area of that rectangle. The 2 is the area of that rectangle, and the 11 is the area of that rectangle. So the distance traveled is 23, which is the combined area of those rectangles. Now, of course, this is a very unrealistic graph, so let's take a look at something slightly different. Let's suppose that the velocity looked something like the following. So the velocity started out at 5.5 miles per hour and decreased over the course of 6 hours to something that was very, very small. Now remember, this is velocity. So the velocity is positive, which means the distance is increasing, and the velocity is decreasing, which means its derivative, which is acceleration, is negative. Now we can estimate the velocity by focusing on small time intervals where the velocity is almost constant. So what we'll do in this example, we'll take the time interval from 0 to 6 and we'll divide it into 12 time intervals of length 0.5. So 0 to 6 divided into 12 time intervals, and then what I'll do is I will draw segments over each of those time intervals. Okay? Now, if each time interval is fairly small, the velocity is almost constant, not quite, but almost constant. So if we think about this as sort of a rectangle, we could take the change in time, which is 0.5, and multiply it by a height, so to speak. Okay. So on each interval, we can approximate the distance traveled over the course of that subinterval by choosing a velocity at any particular instant in time. So, for example, if I look at the first time interval, the velocity is pretty close to 5.5. So I could maybe just use 5.5 as a ballpark estimate for the constant velocity over this time interval. I could do something similar here, something similar here. Now there's different ways to choose the velocity over each subinterval. Sometimes we can use the velocity at the center of the time interval. We can maybe use the largest velocity over each time interval, but what we're going to focus on are two types of estimates. One is the left-hand estimate, where for each time interval we use the velocity at the left-hand endpoint. So for this interval we use the velocity at that endpoint. For this interval we use the velocity at that endpoint, and so on and so forth. So the left-hand estimate uses the velocity at the value at the left-hand endpoint of each subinterval. So we take our velocity at time 0, v of 0, which is that. We'd multiply by delta t, which is 0.5 in this case. The next subinterval, our velocity is pretty close to v of 0.5, which we multiply by delta t. For the next subinterval, the velocity over the time interval is not too different than v of 1, the velocity at the left-hand endpoint, and so on and so forth. Now the very last endpoint, the very last time interval, we're going to be using the velocity at 5.5 hours. Now, we call this L12 because we're using 12 time subintervals, and the way we can actually get the values in this case, because we have a graph, is to estimate them from the graph itself. So for example, v of 0 appears to be about 5.5. v of 0.5 is about 5.3, the height there. v of 1 is about 5. v of 1.5 is about 4.5, and so on. And over here we have v of 5.5, which I estimated to be about 0.25, because this distance is 0.5 and half of that would be 0.25. So I'm taking 5.5 times 0.5. That's an estimate of the distance traveled during the first half hour. I'm taking 5.3 times 0.5. That's an estimate of the distance traveled during the second half hour, and so on. Now I can factor 0.5 out of all of these terms, add the results together, and I get 16.625. And this corresponds to a sum of rectangles where the height of the rectangle over each subinterval is obtained by drawing a horizontal line segment using the velocity at the left-hand endpoint. So let me try to draw this. So what I'm going to do is I'm going to go to the left-hand endpoint of each time subinterval, and I'm going to draw a little segment. Now, the 5.5 times the 0.5 is the area of this rectangle. The 5.3 times the 0.5 is the area of the second rectangle. Notice how the height of each rectangle is being determined by the function output at the left-hand endpoint of each subinterval. And so on and so forth. I won't shade them all because that's going to just take some time and I'll probably mess it up anyway. Okay, so that's what we call a left-hand estimate. A right-hand estimate is defined analogously, except we're always using the right-hand endpoint of each subinterval. So for the first subinterval, we use the velocity at 0.5 hours. For the second interval, the velocity at 1 hour, and so on and so forth. The very last one will be the velocity at 6 hours, which we didn't use in the left estimate. The left estimate used 0 as the first endpoint and 5.5. But in the right estimate, the first endpoint is going to be 0.5 and the last one is going to be 6. They both have 6 terms. So I once again estimated these values from the graph, and you can see how many of the values are the same as above, but the last one, the last rectangle, the height was a little bit smaller. The last rectangle, when I did a left-hand estimate, was 0.25, but when I used the right-hand estimate, I used 0.2. I added these quantities together and I got 13.975, which is less. I'm going to shade the area of these rectangles. Sorry about this. A right-hand sum corresponds to a sum of rectangles where the height of the rectangle over each subinterval is obtained by drawing a horizontal line segment using the velocity at the right-hand endpoint of the subinterval. So for example, this first time interval would look something like that. Second time interval would look something like this. Next time interval would look something like that. And so on and so forth. Notice in this case that when I did the left-hand estimate, I was always adding a little more area. There was always a little bit of area, okay, above the curve. In terms of the distance traveled, both the 16.625 and the 13.975 approximate the distance traveled. And it appears that the distance traveled is going to be something in between. The last rectangle is going to look like that, and the second to last is going to look like that. Okay? So these are two types of estimates. If you take Calc 2, you'll learn about all sorts of other ways of drawing these rectangles. Now we call these rectangle sums, sums of rectangles of this form. We call them Riemann sums, named after the German mathematician Bernhard Riemann. Excuse me, it's easy to mispronounce this word, but it's Riemann. So if you're familiar with the song by Aerosmith called Dream On, that maybe you're not young, maybe you're too young to remember that song, but think about that song Dream On, and it rhymes with that. It's Riemann, Riemann sums. So we start with a velocity function and a given time interval from A to B. Suppose we want to approximate the distance traveled over the time interval using the sum of rectangle areas. Now we take our time interval and we divide it into n time subintervals, where n could be 10, 50, 60, whatever. The length of each subinterval, the change in time, is going to be b minus a over n. And then we label our endpoints, t0, t1, t2, up through n. The number of time interval endpoints, subinterval endpoints, is always going to be 1 greater than n because we count starting at 0. The left-hand estimate is going to be defined as a sum where we begin with the leftmost endpoint and we go up to t sub n minus 1. We multiply each of these quantities by a velocity. So this would be an estimate of the distance traveled during a subinterval, estimate of a distance traveled, so on and so forth. And the right-hand sums are defined analogously, but we use the right-hand endpoint. So the first endpoint is t1 and the last one is tn. Okay, let's look at a simple example. Suppose v of t is t squared plus 3t. The time interval is from 2 to 5, and we want to compute left and right estimates using n equals 6. I've drawn the graph between t equals 2 and t equals 5. If we take b minus a, which is 5 minus 2 over 6, we get 0.5. The subinterval endpoints then, t0, would be 2. This would be t1. 3 would be t2. 3.5 would be t3, t4, t5, and t6. Now, I've made a table of values for the function. The indices from 0 to 6, those are our 7 points. This would be t0, t1, t2, as you saw, and so on and so forth, as you saw them on the previous page. And I took these values of t and I plugged them into the formula for the function. I won't go through the details, but that's what you get for a table of values. So L6 would be 10 times 0.5 plus 13.75 times 0.5 times plus 18 times 0.5 and so on. And the last value we would use is 33.75. We'd multiply each one of these quantities by 0.5, but we could factor that out and we'd get 63.125. The right-hand estimate would be very similar, except instead of starting with the 10 output and stopping with 33.75, we would start with 13.75 and end with 40. So the right estimate would be this term plus that term plus that term plus that term plus that term. We multiply each of those by 0.5. We get 78.125. Now the left-hand estimate in terms of my graph would be rectangle areas. And for each time subinterval, I would draw a rectangle using the left-hand endpoint as my height. So I have 6 rectangles. So again, I'm using the left-hand endpoint for each subinterval. The area of these rectangles added together is approximately 63.125. Now for the right estimate, I do something similar, except now I'm always using the function output at the right-hand endpoint of each subinterval. So the first rectangle would look like that, the second rectangle would look like that, and so on and so forth. And that's what we have. Okay, so we call those Riemann sums. And you can sort of get the feeling that if we use more and more rectangles, we're going to get more accurate representations of the area under the curve. So what I'd like for you to do in preparation for class is I would like for you to calculate the left Riemann sum, L5 and R5, for two different functions. One of the functions is t to the third plus t. Use the interval from 1 to 3, 5 rectangles. So you'll have two estimates, L5 and R5, for this example. And then the cosine of pi over 4t. Now I didn't make that very clear, but it's pi over 4 times t. The 4 is not in the denominator. So pi over 4 quantity times t, cosine of pi over 4t. The interval is from 0 to 2 using 8 rectangles. And for the second function, what I want you to do is I want you to sketch the function, and I want you to shade rectangles whose combined areas sum to L5, and then draw a sketch of V and shade rectangles whose combined areas sum to R5. Okay, so I'll see you in class.